Okay, so we will complete this chapter today. Yesterday we were talking about the second main point, second sub point under the second main point, that is introduction to kernel. Under introduction to kernel, in the day before yesterday we discussed about architecture, and yesterday we were talking about introduction to system concept, and with the help of the second point we were covering third point also. Okay, so last point is very small one, so we'll cover both these points today. So under introduction to system concepts, we discussed the concept of inode, then we discussed the concept of link, then we discussed the concept of kernel data structures of file. So three data structures we discussed: user file descriptor table, file table, and inode table. And then we talked about the file system layout, how the file system is exactly stored on the disk. So it is stored in the form of 4 major blocks. So at the time of installation, we have to partition the total space allocated to the operating system, Linux operating system, into 4 partitions called as a boot block, super block, inode list, and data block. And further, we discussed why this inode list and data block, they are shown as a with the help of dotted line. So their size is variable one. That's why it is variable. That's why it is shown with the help of dotted line. So size of data block is varying throughout the lifetime of the system, as well as size of inode list is also going to vary throughout the lifetime of the operating system. And data about data blocks and inode list is stored inside the super block, and all the files related to booting are stored as a part of boot block. So this is about file system layout in case of Unix operating system. Now come to the next point, next concept, introduction to system concepts. So next concept is of process. So again, regarding process, just a minute. So regarding process, so we already discussed how the process is created. The process is created with the help of fork system call, and each process is identified with the help of unique identification number called as a PID. So when PID is assigned, so PID is assigned during execution of fork system. If the system call is executed successfully, so once the execution is successful, fork system call execution is successful, so process enters in the new state. Process enters in the new state. It is also called as a created state. And immediately one process identification number is assigned by the operating system to that process, indicating you are the unique process. So you are totally identified with the help of this unique number called as a PID. So each process is having its own process identification number. PID stands for process identification number. Okay. So in case of Unix operating system, so initially two major processes are created. One process is called as a swapper. It is also called as a process 0, and another process is called as a init. It is also called as a process 1. Listen carefully. So in Unix, once we boot the system, जेव्हा आपण युनिक्स ऑपरेटिंग सिस्टम किंवा लिनक्स ऑपरेटिंग सिस्टम बूट करतो, बूट करायच्या वेळेस पहिल्यांदा प्रोसेस 0 क्रिएट होते. म्हणजे जेव्हा बूटिंग स्टार्ट होतं, इमिडिएटली process 0 is created by hand by the operating system. It is said that it is created by hand. Automatically process 0 create होते. And the process 0 ला swapper असंही म्हटलंय. And what is the work of swapper? Swapping in and swapping out. So what is required to swap in? जेव्हा आपण ऑपरेटिंग सिस्टीम रन करत असतो, तेव्हा ऑपरेटिंग सिस्टीम रन करण्यासाठी ज्या काही फाइल्स लागतात, ज्या आपण बूट ब्लॉक मध्ये ठेवलेल्या आहेत, त्या सगळ्या फाइल्स स्वॅप इन होतात with the help of swapper. So swapper does swapping in of all these files from the hard disk to the main memory, executes these files, and after execution again these files will be swapped out from the main memory and kept back on the secondary memory. So that's why swapper is created initially. And once swapper is get created, so internally swapper executes the fork system call and creates init process. So these are the two processes. So swapper is not created with the help of fork system call, but init is created with the help of fork system call. Who is the parent of init? Swapper is the parent of init, and further init executes fork system call internally or externally. Internally in the sense to create the system processes, and externally in the sense to create the user processes. Init executes fork system call more than once internally or externally and creates child processes. And all the child processes, they may further use the fork system call to create the subchild like that onwards. Tree-like structure will be there. So swapper is the main parent. After that, swapper executes fork, creates init. So init then executes fork and creates some child processes. Child processes, they will execute fork, they will create subchild. Subchild will execute fork, they will create subchild like that onwards. So like that, here in Unix, init process is called as a main parent. Init process is called as a main parent because init executes fork n number of times and creates the number of processes. Swapper executes fork only once to create init. That's why swapper is not called as a main parent. Init is called as a main parent. Init ह्या प्रोसेसला मेन पेरेंट म्हटलेलं आहे का तर init बरेचसे फोर्क सिस्टीम कॉल एक्झिक्यूट करून बऱ्याचशा प्रोसेसेस क्रिएट करतो. पण स्वॅपर किती प्रोसेस क्रिएट करतो? स्वॅपर फक्त एक प्रोसेस क्रिएट करतो, एकदाच फोर्क सिस्टीम कॉल एक्झिक्यूट करतो आणि कुठली प्रोसेस क्रिएट करतो? इनिट. Okay, so process swapper is also called as a process 0 and init is also called as a process 1. So this is the tree-like structure present in case of Unix operating system. Next, data structures for processes. Under processes, we are discussing about this point, kernel data structures for processes. So these are the data structures. So the diagram is shown over here. So first data structure is called as a U area, second one is called as a process table, third one is called as a per process region table, and fourth one is called as a region table. Actually, these are the four data structures which are used by the processes which are used by the kernel internally for managing the processes. And main memory, it is the part of memory. Okay. So first of all, draw these structures, all of you. I hope you have noted the point. Processes. So this is the second point under the main point, introduction to system concept. Main point is introduction to system concept. Under that first point, that is overview of file system. We have discussed yesterday, and today we are discussing about processes. So how the process is created with the help of fork system call, how it is identified with the help of PID number, which two are the main processes inside the Unix, swapper and init. Swapper is also called as a process 0, init is also called as a process 1, and then draw the kernel's data structures for processes. Kernel's data structure for processes. So all of you draw the data structures related to process. Yesterday we discussed data structures related to file, and today we are discussing about data structures related to process. So these are the four data structures. Actually, main memory is also structure, but it is a big structure. It is not included as a part of data structure. So U area is the data structure, process table is the data structure, per process region table and region table. So these are the four tables. They are keeping the data about the process. So we'll see what kind of data is kept inside U area, what type of data is kept inside the process table, per process region table and region table. Draw the diagram. Harshad Bad is there?
Yes, ma'am.
Draw the diagram. Is it over? Yes, anybody? Are you listening to me? Hello. Hello, students. Are you listening to me?
Yes, ma'am.
Okay. So is it over? Diagram is over? Okay. So listen carefully to understand the concept. So U area, so it is also called as a user area. So the current status information about process is stored inside the U area. Current status information about the process, it is stored inside the U area. What is the current status information? That is, if you think about the state of the process. If you think about the state of the process, so process is going to change the state. So initially it will be in the new state. After some time it will be in the ready state. After some time it will be in the running state, or it will be in the waiting state, or it will be in the terminated state. So these are the, if you consider the state field of the process, it is variable one. It is variable one. So that data is stored inside the U area. So while the current execution is going on, so current status information about the process is stored as a part of U area for a while. Actually, again in the fifth chapter, we are discussing about all the fields of U area. But here we'll just discuss about the overview. So कुठली इन्फॉर्मेशन ठेवली जाते यू एरिया मध्ये, जी करंट इन्फॉर्मेशन आहे, म्हणजे सध्या प्रोसेस चालू आहे आणि त्या प्रोसेस बद्दलचा जो काही करंट डेटा आहे, म्हणजे त्या मोमेंटला जो काही डेटा आहे, that data is stored inside the U area, and actual data about the process is stored inside the process table. Okay. So process table, for example, PID. So PID will be constant throughout the lifetime of the process. Process create झाली की जोपर्यंत टर्मिनेट होत नाही तोपर्यंत त्याचा PID constant राहतो. So जो constant data आहे, so that will be stored as a part of process table, and whatever variable data is there with respect to process, that is stored with the help of U area. So I taken the example of state and PID. So state field is present inside the U area because state is variable one throughout the lifetime of the system, and PID is not a variable one, so it will be constant throughout the lifetime of the system. That's why PID is stored as part of process table. So like that, we are discussing about total 8 fields under the process table and total 12 fields under the U area in fifth chapter. So for a while, just assume that. So what is the difference between U area and process table? So process table maintains data about each and every process present in the system. For example, so if you see over here, जर सिस्टीम मध्ये 10 प्रोसेसेस असतील तर 10 प्रोसेसला रिलेटेड 10 एंट्रीज ह्या प्रोसेस टेबल मध्ये असतील, P1, P2, P3, like that, P10. And out of that only one process will be in the एक्झिक्युशन. 10 प्रोसेसेस मेन मेमरी मध्ये आहेत, म्हणजे त्या 10 प्रोसेस बद्दलचे 10 एंट्रीज ह्या प्रोसेस टेबल मध्ये असणार आहेत, पण त्या 10 पैकी एकच प्रोसेस अंडर एक्झिक्युशन असणार आहे. सो द डेटा अबाउट दॅट प्रोसेस विल बी स्टोर्ड इनसाइड द यू एरिया. म्हणजे so maybe first of all process P1 will be under execution, so the data about P1 will be there as a part of U area, and after some time after P1, P2 will be under execution, then data about P2 will be stored as a part of U area, like that onwards. So the data current status and control information about current process is stored inside U area, and data about all the processes is stored as a part of process table. Further, process table is pointing towards the per process region table. So the name itself tells that each process is having its own per process region table. So actually, there are 3 regions based upon the 3 contexts which we discussed in OS. So process consists of 3 contexts. One is called as a data, another stack, and text. So text region, data region, and stack region. So each process is having three regions. So based upon the context. प्रोसेस तीन कंटेक्स्ट मध्ये डिवाइड केलेले आहे. प्रोसेसचे कंटेंट्स जे प्रोसेसचे कंटेंट्स आहेत ते तीन पार्ट मध्ये डिवाइड केलेले आहेत. एका पार्टला टेक्स्ट म्हटलेले आहे, दुसऱ्या पार्टला डेटा म्हटलेले आहे, तिसऱ्या पार्टला स्टॅक म्हटलेले आहे. सो लाईक दॅट according to these three contexts, three types of regions are there: text region, data region, and stack region. So each process is having minimum three regions. Each process is having minimum three regions. So that's why inside this per process region table, three entries will be there. Minimum three entries will be there. One for text region, another for data region, and third for stack region. Actually, stack is further divided into two types of stack, called as a user stack and kernel stack. User stack and kernel stack. So user stack is used by the process when it is executing in user mode or in user level, and kernel stack is used by the process when it is executing in kernel mode or in kernel level. So we have discussed about the architecture. You are very familiar with kernel mode and user mode, or user level and kernel level. So whenever it is executing in user level, so it takes the help of user stack, and whenever it is executing in kernel level, it takes the help of kernel stack. So these are the four minimum regions which are there with respect to each process or per process. So that's why this per process region table is the local table. It is the private table. So each process is having its own per process region table. So whenever process will get created, this table will be allocated to that process, and whenever process is going for termination, so this table will be get deallocated. What is by this table? This is the kernel's data structure. So it's the structure, it is the space allocated from the main memory. So U area per process table and region table, these are the global tables, and per process region table, it is the local table. Okay, and then from the region table, so it is pointing to the actual region table. From per process region table, it points to the actual region table. So for example, text region. So two processes, they may share text region. So text region is normally called as a shareable one. So in that case, in region table, only one entry will be there, and from the per process region table, so if we assume this is the per process region table of P1, so another P2 will be there. It is also having its own per process region table, and from these two tables, the two pointers will be pointing to the one entry inside the region table, that is text region, because text region is normally shareable one. So text region, data region, and stack region. So stack and data regions are the separate regions, but normally text region is shared by the number of processes. So to understand this concept of shareable, so you may take the help of sorting technique, any sorting technique, that is bubble sort, selection sort, merge sort, etc., which you have discussed in data structure. So if you take the sorting program, so sorting program is divided into number of iterations, right? Sorting program is divided into number of iterations. So these iterations will be treated as one separate processes. So if you observe it number of iterations, so number of iterations are treated as a number of processes, and input given to these iterations is nothing but all the elements. There is whatever numbers we are passing for sorting purpose, whatever elements we are passing for sorting purpose. So the input will be same, only the sequence of that input will be different. So that's why in that input is treated as a part of text region. So text region is shareable one. म्हणजे जे काही इटरेशन्स आहेत, एका इटरेशनला आपण एक प्रोसेस म्हटलेलं आहे. तर सो ऑल दीज इटरेशन्स दे आर शेअरिंग द कॉमन डेटा. So that common data is treated as a text region, right? So like that, text region is normally shareable one. So that's why only one entry will be there inside of the region table, and there will be two pointers pointing from two per process region table towards that entry, or there may be three pointers. It depends upon the number of processes. If there are 5 processes, they are sharing the जर 5 iterations असतील तर 5 ही इटरेशन कॉमन डेटा यूज करतात. So that's why 5 processes, 5 per process region table will be there, and from all these 5, one pointer is pointing towards the only one region table entry, which is related to the text region. So like that, first of all, the data is stored inside the U area. From the U area, it is pointing towards the process table. From the process table, it is pointing towards the per process region table, and from the per process region table, it is pointing towards the region table. So this is the flow, and actually region is nothing but the logical address space. Region is nothing but the logical address space, and that logical address space is get mapped onto the physical address space. Physical address space is nothing but the main memory. Physical address space is nothing but the main memory. So over here we are discussing about virtual memory concept. So that's why all the region addresses are treated as a virtual addresses, and these virtual addresses are mapped onto the physical addresses which are related to the main memory, right? So these are the kernel's data structures for processes. These are the kernel's data structures for processes. So this again here we have discussed about overview. So I said that again in the second section, in fifth chapter and sixth chapter, fifth, sixth, and seventh. So in seventh we are discussing about memory management concepts, and in fifth and sixth we are discussing about the data or the concepts related to process. So over there we are discussing about U area in detail, process table in detail, per process region table in detail, and region table in detail. त्या चॅप्टर मध्ये आपण प्रत्येक डेटा स्ट्रक्चरचे रिलेटेड फील्ड्स बघणार आहोत. तर प्रत्येकाला फॉर एक्झाम्पल यू एरियामध्ये टोटल 12 फील्ड आहेत, प्रोसेस टेबल मध्ये टोटल 8 फील्ड आहेत, पर प्रोसेस रिजन टेबल मध्ये टोटल 5 फील्ड आहेत, आणि रिजन टेबल मध्ये टोटल 6 फील्ड आहेत. We are going to discuss all these fields in detail in sixth chapter. So here we are just discussing about the overview. So for a while you can just keep in mind. So what are the kernel's data structures for processes? So the kernel data structure for processes are nothing but U area, process table, per process region table, and region table. Okay. So we'll proceed further under the process itself. Next concept is context of a process. So context of a process is nothing but contents of the process. So what are the contents? So actually the contents, that is process, consist of text data and stack. And further again it is divided into different type of context called as a user level context and system level context. Normally युनिक्स मध्ये प्रोसेस कशी रन होते, थोड्या वेळासाठी युजर लेवल मध्ये रन होते आणि थोड्या वेळासाठी सिस्टीम लेवल मध्ये म्हणजे कर्नल लेवल मध्ये रन होते. And accordingly the context is divided. So three different types of context are there, called as a user level context, register level context, and system level context. कंटेक्स्ट म्हणजे थोडक्यात कंटेंट्स. प्रोसेसचे कंटेंट्स काय आहेत, तर प्रोसेसचे कंटेंट्स अशा ह्या 3 पार्ट मध्ये डिवाइड केलेले आहेत. युजर लेवल कंटेक्स्ट, सिस्टीम लेवल कंटेक्स्ट, अँड रजिस्टर लेवल कंटेक्स्ट. म्हणजे प्रोसेस is executing in user mode, so it takes the help of user level context. It requires some of the registers of the processor, that is like accumulator, A, B, C, D, H, L, all these registers, general purpose registers and special purpose registers. All these registers are used by the process, so that's why all these registers contents will be again part of the context of a process. And third one, system level context. So some context of process is there which is varying throughout the execution of the process. So again detail part we are going to cover as a part of sixth chapter. 6व्या चॅप्टर मध्ये आपण कंटेक्स्ट डिस्कस करणार आहोत, त्याचे डायग्राम डिस्कस करणार आहोत, त्याच्यामध्ये 3 टाइपचे कंटेक्स्ट डिस्कस करणार आहोत. सो ओव्हर हियर यू कॅन जस्ट कीप इन माइंड व्हाट मीन बाय कंटेक्स्ट ऑफ अ प्रोसेस. सो कंटेक्स्ट इज नथिंग बट कंटेंट्स. सो प्रोसेस मध्ये प्रोसेसचे कंटेंट्स काय आहेत हे आपण डिटेल मध्ये डिस्कस करणार आहोत. ओके. सो डन. Under context switch is there. So you are good familiar with context switch. So in OS we have discussed about the diagram of context switch, that is switching the processor from one context to another context. So while switching is going on, so 2 operations are performed. One is reloading and another is that is saving. So load the context and save the context. So while it is switching from lower priority process to higher priority process, so it saves the context of lower priority process and it loads the context of higher priority process. जर तो lower priority process कडून higher priority process ला प्रोसेसर स्विच करत असेल तर त्यावेळेस त्याला काय करायला लागतं ऑपरेटिंग सिस्टीमला. सो ऑपरेटिंग सिस्टीम हॅव टू सेव्ह द करंट कंटेक्स्ट इन द सेन्स contents of lower priority process, and while it is trying to execute the higher priority process, so before execution it have to load the contents or context in the processor, in the memory with respect to the higher priority process. So this is nothing but about context switch. So same diagram is applicable as a part of context switch. Then process states. So the general view of process state we have covered as a part of OS. OS मध्ये आपण जनरल 5 स्टेट्स बघितलेले आहेत, ज्या की आपण नेम केलेले आहेत न्यू, रेडी, रनिंग, वेटिंग आणि टर्मिनेटेड. But in case of Unix, so these 5 states are further divided into substates. So actually here the fields of view area, etc., which we are going to discuss in detail. Okay, so this is the diagram which we are discussing as a part of process state transition in case of Unix. This is the diagram. So again here in the first chapter we have shown only 4 main states of the process, but in I think in fifth chapter we are discussing about total 9 states of the process. So number of states they are somewhat common like our general concept which we have discussed in OS, but depending upon the user level execution and system level execution, the number of states are increased. So total 9 states are there in case of Unix operating system. Out of 9, 4 are main, and these 4 main states we have shown with the help of this diagram. So all of you draw this diagram, then I will discuss this diagram. So I think this is the last point from this chapter. Okay, so this is the last point. We'll discuss this point and then we'll stop the session. So draw this diagram. So user running, kernel running, ready to run, and asleep. So these are the states: user running, kernel running, ready to run, and asleep. Okay, so these are the names. This is the name of this is user running state. This is about kernel running state. So state number 2, and then third state ready to run, and fourth state asleep. So I have just underlined it with the help of blue color. I have underlined the process names. It's user running, it's kernel running, third one ready to run, and fourth one asleep. So these are the 4 major states with respect to Unix operating system. So listen to me to understand the concept. So whenever the process will be get started in a user level, so again recall the architecture. In architecture we have shown user programs. So we are responsible to write the user programs. We are users. So we are writing the programs, and then we are compiling the programs, and after compilation we are running the programs. So when the process will be running in user level, so it is said that it will be in the user running state. That is state number 1. It is said that it will be in the user running state. After user running state, whenever it invokes any system call. So if you are recalling the architecture, so in between user level and kernel level, system call interface is there, right? It is the boundary in between user level and kernel level. So where it is said that whenever any user process or whenever any process calls system call, जेव्हा system call execution सुरुवात होते, so then it is said that process changes the mode from user running to kernel running. So either it calls system call, or it may calls, or there may be the interrupt. So some disturbance may be there. So again, the interrupts are the standard one. So these are the inbuilt one. So these are the system generated interrupts. So all these are treated as a higher priority process than the user process. So system call as well as interrupt are treated as a higher priority process than the user running process. So that's why it is said that it is changing the mode, it is changing the state from user running to kernel running. Okay. So again, from to kernel running, if you are looking, one arrow is there which is coming towards the same state, that is, and the name of that arrow is interrupt comma interrupt return. Okay. So whenever any interrupt comes, when the process is in kernel running state, so it executes that interrupt immediately and it returns the data towards the kernel. So mostly it is happening very rarely. Very rarely the process processes the interrupts when it is in kernel running. But mostly kernel behaves like a non-preemptive. बऱ्याच वेळेला कर्नल नॉन प्रिएम्प्टिव्ह असा बिहेव करतो, म्हणजे एखादी प्रोसेस जर कर्नल रनिंग स्टेट मध्ये असेल तर तो कुठल्याच हायर प्रायोरिटी प्रोसेसला चान्स देत नाही. So one big reason is there behind it. We'll discuss it afterwards. Then from kernel running, the arrow is there towards the user running state, that is the return. So from kernel running, if process want to do any IO operation, it goes to the sleep state, that is 4-number stage. So the arrow name of that one is sleep in the sense it is going for sleeping purpose, that is waiting purpose. So a sleep state is also called as a waiting state. So here the name given over here is asleep. So either it sleeps inside the main memory or it sleeps on the secondary memory. So sleeping is nothing but waiting state. Running is nothing, kernel running or user running is nothing but running state. Okay. And once sleeping is over, that is IO operation is over, it goes to the ready to run state. So ready to run is equivalent to ready state. So third state over here. So whenever sleeping is over, it will be get wake up by the operating system and it is going to be changed the state from asleep to ready to run, and from ready to run again it is going to the kernel running. Okay, so schedule process. So whenever process has completed the IO operation and coming to the ready state, so from the ready state it is going to the again kernel running state. So after kernel running again, if the execution is over, so if it want to return something to the user, so it goes to the user running state. So like that, these are the 4 major states. And actually, while we are talking about the 9 states over there, after kernel running, if process is totally terminated, so one more state is there called as a terminated state. So that we are discussing in the 5th chapter. Okay. So further, I said that mostly kernel behaves like a non-preemptive. Kernel कसा behave करतो? Non-preemptive. म्हणजे जेव्हा एखादी प्रोसेस कर्नल रनिंग स्टेट मध्ये असते त्यावेळेस कुठल्याच हायर प्रायोरिटी प्रोसेसला चान्स देत नाही. The reason behind it is that, so here if you are looking, okay, so if you are looking over here, I have shown, see, this is the diagram, sample code creating doubly linked list. So you are good familiar with the concept of doubly linked list. So here I have shown doubly linked list. So this is BP, this is BP1, and this is the next node. 3 nodes are there. So right now BP is first node and the empty node is the second node. And I want to insert BP1 in between these 2 nodes. So to insert one node inside these 2 nodes, I have to adjust 4 pointers. That is, this pointer should be adjusted over here. I will show with the help of again diagram. I will use the pen. Okay. So to insert BP1, just listen to me carefully to understand the concept over here. मी हे काय डिस्कस करतेय हे तुम्हाला मी थोड्या वेळानंतर सांगेन, सो दॅट यू विल अंडरस्टँड. आता मला काय करायचंय, मी लिंक लिस्टचा कन्सेप्ट घेतलेला आहे. सो दिस इज द डब्ल्यू लिंक लिस्ट. आणि इथं काय करायचंय, मला हा पहिला नोड आहे आणि हा दुसरा नोड आहे. या दोन्ही नोडच्या मध्ये मला तिसरा नोड ऍड करायचा आहे. Okay, so if I want to add this node over here, so I have to adjust this pointer. So like this, is it right? I have to adjust this pointer. Then this node will be having forward pointer and backward pointer, right? So this forward pointer should be adjusted like this here. Then its backward pointer, this pointer, so this pointer should be adjusted like this. right? And its back pointer should be adjusted like this. So in short, I just want to say that to insert one node in between two nodes, so it is doubly linked list, I have to adjust 4 pointers. मला एक नोड ह्या डब्ल्यू लिंक लिस्ट मध्ये इन्सर्ट करण्यासाठी 4 पॉइंटर ऍडजस्ट करायला लागतात. 4 पॉइंटर म्हणजे 4 इन्स्ट्रक्शन्स. This is the insertion process. So this insertion process consists of total 4 instructions. So if I start this insertion, मी insertion start केलं, जोपर्यंत ह्या चारही इन्स्ट्रक्शन कंप्लीट होत नाहीत तोपर्यंत मी कुठल्याच हायर प्रायोरिटी प्रोसेसला स्विच नाही व्हायला पाहिजे, राईट? सो इफ कर्नल बिहेव्स लाईक अ प्रिएम्प्टिव्ह, जर कर्नल प्रिएम्प्टिव्ह बिहेव केला तर काय होईल? यू विल गेट द सिच्युएशन लाईक दिस. सो बिलो आय हॅव शोन द सेकंड डायग्राम. इथं काय केलेलं आहे, आपण 3 पॉइंटर ऍडजस्ट केले करेक्टली. BP1 इन्सर्ट केला, हा पॉइंटर ऍडजस्ट केला, त्यानंतर हा पॉइंटर ऍडजस्ट केला, हा पण ऍडजस्ट केला, पण अजून हा पॉइंटर ऍडजस्ट व्हायचा आहे, म्हणजे ह्याला पॉइंट करायचा आहे तो अजून बॅक नोडला. म्हणजे ऍक्च्युअली दिस इज पॉइंटिंग टू द प्रिव्हियस नोड ओनली. नाउ अकॉर्डिंग टू द इन्सर्शन, so this node should point over here, right? So but this insertion yet I have not completed because I have not executed this last instruction, and at that time context switch occurred. Context switch म्हणजे काय? हायर प्रायोरिटी प्रोसेस आलेली आहे आणि कर्नलला चान्स हायर प्रायोरिटी प्रोसेसला दिलाय, तर काय होईल? ही जी इन्सर्शन ऑपरेशन आहे ही इथंच थांबेल and it will give chance to the higher priority process. It means if you observe this data, this linked list, so this is called as an inconsistent linked list. This is called as a inconsistent. हा consistent डेटा नाहीये, हा प्रॉपर डेटा नाहीये, हा व्हॅलिड डेटा नाहीये. का तर याचा एक पॉइंटर करेक्टली पॉइंट केलेला नाहीये. ऍक्च्युअली तो कुठं पॉइंट व्हायला पाहिजे? BP1 ला, पण तरी पण तो अजून BP लाच पॉइंट होतोय. का तर ही ऑपरेशन कंप्लीट न होता कर्नलनं काय केलेलं आहे? कंटेक्स्ट स्विच केलेलं आहे, म्हणजे प्रोसेसर ह्या प्रोसेस कडून हायर प्रायोरिटी प्रोसेसला अलोकेट केलेलं आहे, राईट? सो इफ कर्नल बिहेव्स लाईक अ प्रिएम्प्टिव्ह, so this problem may occur. This is treated as a problem. This problem may occur, and that's why what kernel does, kernel will not behaves like a preemptive frequently, so it behaves frequently as a non-preemptive. Non-preemptive म्हणजे जेव्हा ही इन्सर्शन ऑपरेशन किंवा डिलिशन ऑपरेशन, तुम्ही आता इन्सर्शन घ्या किंवा डिलिशन घ्या, म्हणजे हे कशासाठी करायचंय? आपण काय करतोय नॉर्मली, what we are doing normally, once we start the machine, we are reading the data from the hard disk and we are writing that data back to the hard disk, right? हार्ड डिस्क मधून म्हणजे ब्लॉक मधून डेटा रीड करतोय कुठं? बफर मध्ये, आणि बफर मध्ये जर मॉडिफाय केला डेटा तर तो बॅक राईट करतोय आपण. म्हणजे इथं काय करतोय आपण? बफर मॉडिफाय करतोय, आणि मॉडिफाय केलेला बफर जर मी मॉडिफाय केला असेल, एखादी फाईल जर मी मॉडिफाय केली असेल, तर तो बफर मला बॅकला राईट करायला लागतो हार्ड डिस्कवर. ती फाईल मला सेव्ह करायची आहे. हार्ड डिस्कची कॉपी डिफरंट आहे आणि मेन मेमरी मधली कॉपी डिफरंट आहे. So if I want to save that data, so I have to perform the read and write operation, and while I am performing the reading and writing operation, so I may take the help of buffers. मी एखादी फाईल रीड करत असेल आणि फाईल जर if file is greater than one block, so I need to I require one more buffer, right? 512च्या ऐवजी 512 पेक्षा जर ग्रेटर असेल फाईलची साईज, तर मला ती फाईल रीड करण्यासाठी 2 बफर लागतील. येते लक्षात? 512 असेल तर एका ब्लॉक वरून एका बफर मध्ये मी रीड करेन. 512 पेक्षा जास्त असेल तर अजून एखादा बफर लागेल मला. तर मी काय करणार आहे, हे जे बफर्स आहेत ते फ्री लिस्ट मध्ये ठेवलेले आहेत, त्या फ्री लिस्ट मधून मी त्याला डिलीट करणार आहे आणि ऍक्टिव्ह लिस्ट वर ठेवणार आहे. टू टाइप्स ऑफ लिस्ट आर देअर. वन इज free list of buffers and another is active list of buffers, right? So that is deletion from the free list and insertion on the active list. So these operations are going on during reading writing operation, and these are the frequently required operations. So that's why kernel behaves like a non-preemptive. So again, detailed part we are going to cover again as part of second chapter. For a while actually I discussed over here only this part. Actually I discussed this one, that is I was talking about this point. हा पॉइंट मी डिस्कस करत होते, जेव्हा कर्नल रनिंग मध्ये एखादी प्रोसेस असते ती नॉर्मली ती प्रियम्प्ट केली जात नाही, ती कंटिन्यू केली जाते, ती कंप्लीट झाल्याशिवाय कर्नल दुसऱ्या प्रोसेसला कंटेक्स्ट स्विच करत नाही. सो दिस इज द रिझन behind it why kernel behaves like a non-preemptive. So just keep in mind, kernel behaves like a non-preemptive when process is running in kernel running state. जेव्हा एखादी प्रोसेस कर्नल रनिंग स्टेट मध्ये असते त्यावेळेस कर्नल कसा बिहेव करतो, नॉन प्रिएम्प्टिव्ह. नॉन प्रिएम्प्टिव्ह म्हणजे जेव्हा ती प्रोसेस कर्नल रनिंग स्टेट मध्ये असते तेव्हा कुठल्याच हायर प्रायोरिटी प्रोसेसला तो कंटेक्स्ट स्विच करत नाही, त्या प्रोसेसला वेट करायला लावतो. आणि जेव्हा ती प्रोसेस कर्नल रनिंग स्टेट मध्ये त्याचं एक्झिक्युशन कंप्लीट होतं तेव्हाच इट विल लूज द कंटेक्स्ट स्विच. So this is the reason. Okay, so this is about process state, and this is nothing but about the end of this chapter. Once again, I will revise this concept in second chapter. It is required over there. So next concept is sleep and wake up. So sleep is nothing but waiting state, and waking up is nothing but changing the state from waiting to ready to run. Okay, so wait system call is used for that purpose. So kernel data structures, most kernel data structures occupy fixed size tables rather than dynamically allocated space. So just now we discussed total 7 data structures. So 3 related to file and 4 related to process. And as a part of system administration, last point, disk formatting, creation of new file system, repair of damaged file system, all comes under system administration. Okay. So system administration म्हणजे काय, जर मी ऍडमिनिस्ट्रेटर असेल तर मला काय करायला लागतं, जर सिस्टीमची डिस्क फुल झाली असेल तर डिस्क फॉर्मॅट करायला लागते, सिस्टीम क्रॅश झाली असेल तर ती मला परत एकदा इन्स्टॉल करायला लागते किंवा रिपेअर करायला लागते. Creation of new file system. So I may install the system newly. जर करप्ट झाली असेल तर परत एकदा मी न्यूली इन्स्टॉल करेल, अदरवाइज आय मे रिपेअर इट. सो 2 ऑप्शन्स विल बी देयर. सो वन्स अगेन इन्स्टॉलेशन by formatting the total disk and or repair of damaged file system. काही फाइल्स करप्ट झालेले असतात त्या केस मध्ये आपल्याला रिपेअर करायला लागतं. सो ऑल these options are coming at the time of installation. Okay, so this is about system administration. So with this I have completed the first chapter. So any doubt about first chapter? Hope you are listening to me. Yes, nobody is listening.
No, ma'am, no doubt.
Okay, so I will share the notes, these notes with you people. Everything is there in these notes. So we'll stop here today. Your session is there, that is by our Prime Minister. The Charcha on Pariksha Pe Charcha. So they are going to discuss. So you have to join that session immediately. Actually, it is said that before 5 minutes you should join. So I'm leaving the session, my class in time. So all of you write your attendance in the chat box and you can leave and you can join that session. So it is scheduled at 11 o'clock sharp. I think link is shared with you people on the group. So write your numbers in the chat box as a part of attendance and you can leave.